Okay, I think I'm ready.
Hi, Reddy, I'm Dad.
What I really meant is that I'm Pedro Rodriguez, and today we're going to explore how NLP leaderboards and benchmarks can be improved by a method called item response theory.
Our approach is called difficulty and ability discriminating leaderboards, DAD for short.
Leaderboards are a way to measure progress in NLP on important tasks like question answering and natural language inference. They consist of a benchmark task, a metric to measure progress, a ranked list of models, and for simplicity, let's meet two models, Bert and Ken.
Kin is pretty smart, but there's a new upstart, Bert, who wants to challenge Kin on the leaderboard.
Over the past several years, for better or worse, leaderboards have grown in popularity and importance.
But leaderboards aren't perfect. Just because one model does better than another, it doesn't mean that it is better. Moreover, aside from getting a ranking and a number, a leaderboard doesn't tell you why a model is better. Dad tries to fix this.
We're going to make our case using the squad leaderboard.
Hi, I'm Robin, one of the researchers behind the Squad Leaderboard. We created this leaderboard to test how well models can answer questions about passages from English Wikipedia. Models answer by highlighting a word or phrase from the passage and are scored by comparing their highlighted answers to reference answers. If they match, they get a high score. Otherwise, they'll get a 0, like in this case. To submit to the leaderboard, system developers submit a runnable system. We feed these systems both development and test questions, get the system's predictions, score each prediction, and record the scores. Finally, we sort the models by average accuracy to create the Squad Leaderboard.
So how is DAD different from existing leaderboards?
First, we expose a fundamentally incorrect assumption in leaderboards. Then, we'll use something called item response theory to address this problem. Then, we'll try to convince you that it is an effective way to rank models, improve annotation efficiency, and identify bad examples.
When leaderboards take the average of metrics like accuracy, they assume two things. One, that questions are equally informative of how good a system is, and two, that the usefulness of a question is independent of how good that system is.
Let's go back to these two systems, Bert and Ken.
We ask both of these systems the same question. There are 4 possible outcomes. 1, they could both get the question correct, in which case I learn nothing about who is better at answering questions. 2, they could both get it wrong, and again, I learn nothing. Or one of them gets it wrong, and I know that the other one is thus probably better. Suppose that the probability a model gets a question correct is PC. You could then multiply these probabilities out to get the probability of each cell in this 2x2 table. Because the diagonal is the best for us, this is maximized when PC is equal to 1/2. Let's now bring in the first D in DAD, difficulty. Suppose questions can vary in difficulty. Let's say that Ken beats Bert only on medium difficulty questions. If there aren't enough of those questions in that sweet spot of the diagonal that we just saw, you won't be able to tell whether Ken is actually better than Bert. And that's the second D of DAD, discrimination.
But how can we identify which questions are discriminative? To solve this challenge, we took inspiration from decades of research in educational testing, a field that specifically develops methods for comparing the ability of humans based on standardized exams, like the GRE, SAT, and TOEFL. In tests like these, participants called subjects answer questions called items, and practitioners rank these subjects by their performance. Doesn't that sound a lot like what we're trying to do with NLP models? In IRT, there are 3 key elements. Items, or in NLP terms, questions and examples. 2, subjects, or in NLP terms, models and systems. And 3, responses, or in NLP terms, scored predictions.
The math can look a little intimidating, but it's fairly simple. Let's start with the most important properties of subjects and items, the subject skill, or ability, and the item difficulty.
All of this will get turned into a probability of a subject answering the question correctly.
This looks a lot like a logistic regression.
You can think about these terms as features the model is learning.
Each question can be more or less difficult. The more challenging the question, the higher its beta I.
When the skill minus the difficulty is high, the higher the probability of the subject answering it correctly.
This is a bit of a simplification. Let's add some additional terms to the equation.
Discriminability shows how well the question distinguishes better from worse systems, and feasibility is related to whether it is possible to get a high score on this item at all. The key equation in IRT relates each of these parameters to the likelihood of a correct response. Let's begin with the exponent. Due to the negative sign, as the exponent gets large, the exponential term goes to 0, which brings the probability of a correct response up. What makes the exponent larger? If the margin between a system's skill and a particular question is high, then the exponent is also large. Similarly, even if the margin is small, if a question is highly discriminative, then the exponent is also large. Let's see how these play out graphically on a plot called the item characteristic curve. In this plot, we hold the difficulty constant at 0 and track how skill is related to the probability of a correct response. As the skill, theta, increases, this likelihood goes up to the feasibility of the question. Each of these three lines shows how this likelihood changes as we change the discriminability. If we have a very small skill difference, say between 0 and 1, how easy is it to tell that these models are different? With a highly discriminative item, like one with discriminability equals 2, it is easier to detect this difference.
But how do we figure out the parameters of each question and of each subject?
Given a bunch of data, questions, and how subjects answer them, we can find the parameters that best explain the data.
We're not going to give you all the details here, but short version is we're doing mean field variational inference.
There are many things you can do with IRT. In this paper, we show a few proof of concepts. However, in this video, we focus on these three. For more details, see the paper.
Hey Pedro, I have a bunch of models and I want to know when they're going to answer a question correctly or not. Can Dad help?
Yes, IRT models do accurately predict whether NLP models get squad questions correct. To predict responses, we try 4 IRT variants of increasing complexity.
Can Dad help me create a better ranking over models if I don't have much data for my test set?
Yes, IRT can improve the reliability of leaderboards. A key component of leaderboards is ranking models by how good they are. The main idea in this experiment is to see if ordering models by IRT skill is more reliable than mean accuracy regardless of how large your test set is. So we use the score dev predictions from Squad and score test predictions. For each of these, we rank models by mean accuracy and IRT skill. From these rankings, we compare, with Kendall-Tao's correlation, how stable IRT rankings are from dev to test, and compare them to how stable accuracy rankings are, which is that ranking by IRT skill, the blue lines, is modestly more stable than accuracy, the orange line.
But I want to create a new data set where annotating whether a subject's answer is correct or not is pretty difficult or expensive.
To test this, we study a case where we have n subjects, m items, and scores for all their responses. We also assume that evaluating a response, like you mentioned, is expensive, as it is in dialogue and machine translation. Continuing on, our experiment posits that we have k new subjects that we want to evaluate. Our goal is to annotate items for these k subjects while minimizing your annotation costs and maximizing the reliability of the resulting ranking. We take n plus k subjects in the Squad leaderboard and split them into 2 groups, 80-20. Then, for a variety of target number annotations, we select items using different sampling methods. In this experiment, selecting randomly is the baseline, and we compare against choosing the most difficult, most discriminative, and most informative items. Similarly to the rank reliability experiment, we compare the reliability of rankings generated by the selected examples.
You mentioned sampling the most informative examples. How do you define informativeness?
Let's think back to before, where we wanted to compare Ken and Bert, and noted that whether we find one is better than the other depends on the likelihood of a question being answered correctly. Intuitively, this corresponds to maximizing PC times 1 minus PC.
And we can turn that into a mathematical formula we can call informativeness. And so the more discriminative a question, the higher the gamma.
This figure shows the correlation of ranking by the sampled items to the final test ranking. The yellow line shows that sampling by information maintains a stronger correlation outside of the low sample regime, where sampling by discrimination based methods does best. Intuitively, always picking the most difficult item isn't helpful either, since it is likely to tell you nothing about whether Ken or Bert is better. We can also test how IRT can play a role in leaderboard visualizations. Even though we won't discuss the visualization in detail in this video, we'll show you the results of this type of analysis next. In our last experiment, we use IRT to identify bad examples. We sort squad examples by high difficulty, low difficulty, high discriminability, most negative discriminability, discriminability near zero, and IRT model errors. This figure shows all the results grouped by how we chose examples. The most clear trends are that examples with negative discrimination and IRT model errors have the most flawed or wrong examples. This question has negative discrimination, which means that as a model skill goes up, the IRT model would predict that the probability of a correct response goes down, which should not happen. The question asks, why did the demand for rentals decrease when the demand for higher quality housing increased, clearly contradicting the question's premise. In the second example, we show a high discrimination item. After inspecting model responses, it was clear that the source of difficulty is that there are several plausible answers, in this case, noun phrases, to the question. For example, some models answer the Armenian state. Thanks for watching, and learn more about our paper at irt.pedro.ai, and hopefully in the future that will make it less difficult to have discriminative leaderboards.